This is the assignment 502.2, Momentum and Impulse Problem Set. The question says, for question 1, says Michael Scott is dropping identical watermelons from the roof of the Dunder Mifflin building that is 4.5 meters tall. The first watermelon lands in an inflatable castle and doesn't break, but the second watermelon lands on Stanley's car and cracks open. Assume the car and castle surfaces are at the same height, and that neither watermelon bounces after impact. How does the air-filled castle protect the watermelon compared to the ground or the metal body of Stanley's car? And so here you're looking at the difference basically in the type of surface that this watermelon is contacting upon impact. And with something like a bouncy castle, which is what this is describing, an inflatable castle, there's some give to it, kind of like an airbag, what that would have in a car crash. And we've talked about that example quite a bit, hitting something that has give to it versus hitting something that is very rigid. And so what's happening here is that both of these watermelons have the same mass. Both of them, if they are dropped from the same height, would have the same change in velocity because they would accelerate from that height until that point of contact. And so with the same mass and the same change in velocity, these two watermelons are also going to have the same change in momentum, because again, change in momentum is mass times change in velocity, and so they'll have the same change in momentum, which also means they have the same impulse. And so it's not the impulse that is being affected here, okay? Rather, it is the time, okay? Because the impulses are equal, but the forces are not going to be equal because the times are not going to be equal. In a situation where you have a larger amount of time for the watermelon to come to a stop, which is going to be the situation if you hit something with some give to it, like that bouncy castle, there are going to be smaller forces experienced by the watermelon. Whereas if the time that it takes to stop is instant, like it would be if you hit a hard surface like a car, then you're going to have that small time but a very large force, because again, those impulses are equal to each other. And so looking at the answer choices here, again, it wants to know how the castle protects the watermelon compared to the metal body, and it does so by lengthening the stopping time and thereby reducing the force that it experiences during landing. This right here would be what you would see for the bouncy castle versus what you would see when it hits his car. Okay, so again, it's very similar to some of the examples from the notes, or like an airbag, hitting an airbag versus hitting the windshield. The example that we used in the notes was that truck that hit a pile of hay versus hitting a wall. It's the same idea. Okay, if it has give to it, then it gives you more time to stop. Greater time means less force. Which experiences a greater impulse? As we just said, they are both equal because it's the same mass if they're identical watermelons, and it's the same change in velocity because they both are dropped from rest from the same height, and so they would both be moving at the same speed at the point of impact, and of course they would both come to a stop. Which experiences a greater force? Again, if you have it happen in a short period of time, the force experienced will be greater, so that's the watermelon on Stanley's car. All right, let's look at the next question, question 2. A hammer strikes a nail. Which best explains the scenario in terms of impulse, change in momentum, force, and impact time? And so our options here are the nail experiences the same change in velocity as the hammer. The nail experiences the same change in momentum as the hammer receives a smaller impulse than the nail receives a smaller impulse than the hammer. So looking at our options here, okay, whenever you have a hammer striking a nail, of course, we know that there's a force pair. We know that the force on the hammer equals the force on the nail, okay, and if the forces are equal, okay, like we've talked about before, that means mass times acceleration of the hammer equals mass times acceleration of the nail. Now, of course, they don't have the same mass. A hammer has a much larger mass than the nail does, and therefore the acceleration of the hammer would be much smaller than the acceleration of the nail. Okay, so we do know that they would not have the same change in velocity because they don't have the same acceleration, and those impacts take the same amount of time. So we can't choose the first one. The second option says the nail experiences the same change in momentum as the hammer. And just as a reminder, change in momentum, mathematically speaking, is the same thing as your impulse. And so these next three choices are basically, hey, the impulses are equal. The hammer has a smaller impulse, the nail has a smaller impulse. Those are our options that we're looking at now. And again, as I've already talked about, the forces are equal. The force on the hammer is equal to the force on the nail. And it's impossible for the hammer to contact the nail for a different amount of time than the nail contacts the hammer. If one is touching the other, then they're touching each other. So they have the same force. They also have the same time of the collision, which means that the force times time for the hammer equals the force times time of the nail. They have to be equal. This is equal to this. This is equal to this. So of course the impulses are also equal to each other. And so if impulse is equal, so is change in momentum. The nail experiences the same change in momentum as the hammer. Question 3 on 502.2 says, as a safety inspector for a car manufacturer, 2 prototypes have been suggested for mass production, but you must pick one. When tested, car Alpha hit the brick wall and bounced back, whereas car Bravo hit the brick wall and stopped on impact. If car Alpha and Bravo have identical masses and the same impact times, which car would you suggest is best for mass production given your role as a safety inspector? Okay, and we talked about this in class as well. Something that hits and stops versus something that bounces back. Okay, if you have something, let's say they're both moving with the same initial velocity. Okay, so let's just make up a number, and let's say that they're both moving with an initial velocity of 20. Okay, positive 20, they're going forward. Okay, the one that stops, let's go with car Alpha first. So Alpha, okay, bounces back. So its final velocity, if it bounces backwards, okay, then it would have a final velocity that is negative. Let's just say it bounces back with a velocity of negative 10 meters per second. Whereas car Bravo stops, so its final velocity would be 0. Okay, again, just looking at these example numbers for a second, my change in velocity for car Alpha is going to be a change of negative 30, whereas my change for car Bravo is just negative 20. Regardless of how fast this moves when it bounces back, it doesn't matter. If it bounces back at all, it's going to have a greater change in velocity than this one. Bouncing is a bad thing when it comes to safety. We talked about it with paintballs and water balloons. You don't want it to bounce off of you. Okay, and so if you're the safety inspector, you would want to choose the one that didn't bounce. And the reason you want that is because it's going to have a smaller impulse. It's going to have smaller force because you have a smaller change in velocity if the one for the one that stops rather than bounces. And so let's see. Alpha bounced back, so it has a larger impulse, and so you would rather choose Bravo because it experienced a smaller impulse. Question 4. An American football player experiences 3,120 newtons of force in a collision. If his helmet comes off during the play, his head stops in only 0.005 seconds during the impact. If wearing a helmet causes the time to be 2 times longer, how does the force of the collision compare? Okay, so again, if he's moving with given set of conditions, that impulse is determined based on his mass, which isn't changing, and his change in velocity. Okay, again, and it's asking us to compare the exact same scenario. So we have the same mass and the same change in velocity. Thus, these will have the same impulse. The impulse is determined by the conditions that we just talked about. But impulse is equal to force times time. And so although the impulse will be the same, whether or not he has a helmet on, that helmet is going to help protect him because of the way that it affects the time and thereby affects the force. If you have a time that is 2 times longer, and it's going to give you the same impulse over here, your force would have to be half as much so that you have the same impulse. Okay, force and time are inversely proportional to one another. That's why when we write them, they end up looking like this. Small force, large time, large force, small time. Okay, same idea here. If the time is 2 times longer, you would have half the force in the collision, half as much. It's an inversely proportional relationship. Question number 5 says high speeds are responsible for the majority of injuries during car crashes today. A car that has more initial momentum will experience a greater impulse when brought to a grinding halt. If two identical cars, A and B, are involved in two separate crashes, if both collisions have the same impact duration of 0.005 seconds, but car A experiences 3 times the force, how does the impulse of car A compare? Okay, so these cars aren't crashing into each other. This is not the same scenario where we have equal impulses to each other. Okay, this is talking about a situation where these two cars are in two separate crashes and they don't necessarily have the same impulse to begin with. Okay, in fact, it tells us that a car with more initial momentum will experience a greater impulse. And we have these two separate crashes, and it tells us they take the same amount of time, but one of them has more force. So automatically, if they take the same amount of time, but one of them has more force, they're not going to have the same impulse. And so it wants to know how the impulse of car A compares if it experiences 3 times the force. Well, if the time is the same for both, but you have 3 times the force here, then of course you're going to have 3 times the impulse, because force and impulse are directly proportional to one another. This is question 6 on the assignment 502.2. Mrs. Begg was having a bad day and kicked a 2-kilogram trash can and a 4-kilogram chair. If she uses the same force both times, compare their change in velocity. Okay, and so just thinking about this logically, because this is something you've probably experienced, maybe not with a trash can and a chair, but applying forces, the same amount of force to objects that have different masses. Okay, and you should already know, and we talked about this in the last unit as well, that if you apply a force to 2 different objects and one of them has a larger mass than the other, that object is going to be harder to accelerate. That 4-kilogram chair in this question has more inertia. It's harder to get it to accelerate than a 2-kilogram trash can. And so if she uses the same force, okay, again, F equals ma. Okay, if she uses the exact same amount of force for both of them, and you can plug in fake numbers if you're not sure. Let's say it's 20, pick a number, it doesn't matter. Okay, and you have a 2-kilogram trash can versus that same 20 newtons applied to a 4-kilogram chair. Okay, again, look at it. Use fake numbers. Okay, but this one would give you 10, whereas this one's going to give you only 5. Okay, so when you double that mass, you get half as much change in velocity, half the acceleration. Okay, and so it wants us to compare their changes in velocity. That trash can will have a change in velocity that is 2 times greater. It will move 2 times as fast compared to that larger chair, a more massive chair. This is question number 7 on 502.2. It says, Fez shoots an arrow with a mass of 0.52 kilograms from a bow. The arrow is initially at rest. The bow exerts a force of 146 newtons for 0.28 seconds. What is the impulse that the arrow receives? Okay, so impulse, again, the equation we're using for impulse is J equals F times T, but we also know that impulse is equal to change in momentum, so it's also equal to mass times change in velocity. Depending on the information that we receive in the question, we could use either of these equations. If we have force and time, we can use force and time. If we have mass and change in velocity, we use mass and change in velocity. Looking at this particular question, I do have the mass, I don't have the change in velocity, so I can't use this, but I do have both of these, force and time, and so that's what we're going to do. We're going to say impulse equals, the force is 146 newtons, the time is 0.28, and that's what we're going to do, is multiply those two numbers in order to get the impulse. 146 times 0.28 gives me an impulse of 40.88. And my impulse is going to be in units of Newton seconds. By the way, a Newton second is the same thing as a kilogram meter per second mathematically, because a Newton is a kilogram meter per second squared. If you multiply that by a second, one of those seconds cancels, you get this. I believe it does accept both units. if you were to put them in here, because they are effectively the same thing. But for impulse, we typically use Newton seconds, and for momentum or change in momentum, you'll typically use kilogram meters per second, but they are technically the same. All right, question number 8 says, as you can see in the diagram above, a ball bounces off of the wall. The force it receives from the wall over time varies according to the graph shown. What is the impulse the ball receives from the wall? This is a force time graph, and on a force time graph you can find your impulse by finding the area, because impulse is force times time. Okay, if you had a constant force, you would simply find the area of that rectangle or multiply those values, but we have a changing force here, and so you're going to find area of this triangle. The formula for area of a triangle is 1/2 base times height. The base of the triangle I have here is 8, the height is 4, and so 1/2 8 times 4, okay, half of 8 of course is 4, 4 times 4 is 16, would be the impulse that it receives. And so let's go ahead and do that. 16. My impulse again is in units of Newton seconds. And the direction of the impulse, well, the direction of the impulse is in the same direction as the force. The wall, it only pushes back with a normal force perpendicular to its surface. And so the force that the wall exerts, it would be actually along this dotted line here. The force would be directly up. In the picture, the way that it's drawn here, I'm aware the ball's bouncing off this way. The wall's not pushing it sideways. It's a flat surface. All it's going to do is apply that normal force perpendicular to its surface. This is question number 9. It says, a softball with a mass of 0.24 kilograms moves at a speed of 17 meters per second. Then the ball is hit by a bat and rebounds in the opposite direction at a speed of 25 meters per second. What is the change in momentum of the ball? The formula for change in momentum, or delta P, is mass times change in velocity. But again, change in momentum is also equal to impulse. So if we had force and time, we could also use that to answer this question. However, in this particular question, we don't have force and time. We do have mass, and we do have 2 different velocities. Again, change in velocity is going to be final velocity minus initial velocity. In this particular question, we have a situation where we have a ball that's initially moving 17 meters per second in one direction and then hits a wall, and after that collision, after that impact, it's now moving 25 meters per second in the other direction. The fact that it's in the other direction matters because that means it has the opposite sign. If I call this positive, this is negative. And so my change in velocity isn't just from 17 to 25, it's from 17 to negative 25. Okay, and so if you want to do that, again, final minus initial, it's going to be negative 25 minus 17. You end up adding these together, okay, because they're both the same sign when you write it like that. Okay, so negative 25 minus 17 is negative 42. Okay, and so it doesn't actually tell us which way is which, so I don't know if these are supposed to be positive or they're supposed to be negative, okay, because it doesn't say, it just says speed of 17. It doesn't say it starts out positive and goes negative. This could be negative, this could be positive. It's not clear. But regardless, the change in the magnitude of my change in velocity is 42. So when I go to solve for my change in momentum, again, delta P equals, my mass here is 0.24, and my change in velocity is 42 or negative 42. I believe it actually accepts either answer here, okay? But 0.24 times 42. So let's multiply that times the mass, 0.24, and we get 10.08 or negative 10.08. Let's try it with the negative because that's what I have on my paper. And my units, of course, change in momentum are momentum units, kilogram meters per second. And again, I think it actually accepts it either way. It does. Okay. Question 10, last one, says the velocity versus time data table below represents the motion of a 4.8 kilogram object. Determine the force acting on the object from 2 to 5 seconds. Okay, so looking at this data table from 2 to 5 seconds is all we care about. Okay, well that first of all is a time window that is 3 seconds long. Okay, I'm only looking at 3 seconds of data here. My initial velocity at 2 seconds is 4 meters per second. It says so in the table. My final velocity at 5 seconds is -2 meters per second. Again, it says so in the table. I have a mass of 4.8 kilograms. Okay, and so this is the information that I'm going to use in order to find force. Okay, well, I've got force, mass, change in velocity. I've got two velocities, time. I'm going to be using my equation F times T equals M times delta V. That's the formula we're going to use. Okay, and so we're going to say, I wish I had more space to write. We're going to say F times my time, 3, equals my mass, 4.8, times my change in velocity. Well, my change in velocity, again, is VF minus VI. So my final is -2, minus my initial, which is 4. That's a change of -6. And so we're going to multiply this by -6. Okay, so 4.8 times -6. And then we need to divide that by 3 so we can get this by itself. Gives me a force of -9.6 newtons. And that is the last question in the assignment 502.2.